Okay, so let me talk about the last one of the colligative property we call osmotic pressure. Now, what's the osmotic pressure? Have you put a vegetable in a salt water? We call pickle, right? Pickle. What's happened to the vegetable in salt water? They lose water, right? They soften up. And this is why we actually, Koreans are making kimchi, right? Kimchi, they put a lot of salt to the napa vegetables. They become softened up because they dehydrate. So it's almost like there's a membrane, and if you put a higher salt in the outside, inside of the cell, they start to lose the water. So what used to be a fatty, juicy, the vegetable became very soft and dehydrated. Right? So it's like a pump, like you can suck the waters out. And so, and then the most commonly used diagram is this one. So let's suppose you have this membrane. This is like a cell wall. You can what we call the semi-permeable membrane. So only the water can go in and out, not the solute. Okay, and then this is like a two compartment. And if I put solvent A, let's say water, and if I put it up, let's say I'll just put it up this way. Let's say, I'm not talking about even solution, I'm just talking about pure water A. It's just a membrane that water can go back and forth. If this is started before, what you see here is, you already know that this is coming down until the levels are the same. You guys know that, right? If you have two bottles of higher and lower, because this is a pressure, so they're being pressurized, so they can move it out so until the same level. In a fancier way, if I write this, if I have a higher pressure than when there's the same pressure, this is an extra pressure that increases the chemical potential of liquid here. That's a fancier way of saying it. What you used to see is a different level, they level up. But what that means is the chemical potential on here, and this is an extra chemical potential, we call the osmotic pressure. And then this one is now chemical potential of an A, but not at the pressure P, but pressure plus I. So it's a pressure-dependent chemical potential term to allow us for you to have an extra pressure here. And whereas the other side here is a chemical potential of P. And this one doesn't make sense if everything is pure here. But if this is a pure, this is not pure. Right? It used to be pure, but not pure. Now what happened? This is a solution, used to be pure, there's a lowering the chemical potential. Now putting an extra pressure, you actually increase the chemical potential. So it's kind of compensate. What used to happen before, and you already know, I'm writing the equation very simple way. Right? So that is the lower chemical potential than your pure water, right? But now what I'm saying that this one is now under different pressure. Not at pressure, but pressure pi. And then this reduction in chemical potential can be compensated. So that's the idea. Okay? So that's one way to say it. I need to explain this in a different angle. So what is this dotted line? We call semi-permeable membrane. So what that means is only A can go through, go back and forth. B is not allowed to pass in and out. So only, that's why the semi-permeable, permeation is allowed for the solvent only. So I'm saying that if this is a water here, water can do whatever they want, they can go in and out. But if you put a sodium chloride, sodium cannot pass through, so does the chlorine ion cannot be passed through. Okay? Does it make sense? I thought the water is bigger than sodium plus. Am I right? I'm checking you guys. This is true. I'm trying to give a very simple logic that, okay, chlorine is like this, whereas water is at least looks like that. Right? Maybe they can small it up to both in and out, right? This you're forgetting about the concept that I didn't talk about, which is sodium is surrounded by water molecule. So the effective volume is a lot bigger. It's what they call the ion hydration. So ion is not naked ion in vacuum. In vacuum is the sodium plus, but you're putting in a water, right? Water has oxygen is negative, hydrogen is positive. So sodium plus, oxygen head is sticking to themselves. So it's like this diagram of sodium, although it's a small, oxygen is, oh yeah, I like you. Right? And they're gonna dock themselves. So this one now, all of a sudden it makes sense why the sodium is not really naked sodium, but it's a hydrated sodium. And it must be bigger than sodium plus the H02 itself, right? It's a much bigger aggregate, so they cannot pass through, whereas H2O is the one is allowed going in and out. So to establish the same chemical potential for left side and the right hand side, and I want to emphasize for the last time here, I'm just talking about this is a pure situation, okay? This is a solution. Okay. So this is a pure A, chemical potential of A at pressure P. Right? And then this is a same pressure P, but overall pressure they're feeling it here is a P plus pi. Okay? So that's an extra pressure. So that's another way. And then another way to think about it too is, I guess we need a little break before I went to the actual long derivation. Think about this. This is your vegetable, right? That's your vegetable. You put a lot of salt, right? And then the vegetable wants to lose the water, because the chemical potential solution is lower than what's inside of the vegetable. Right? But what you want is, let's say I don't want that to be happen. You can make that not happen when you pickle your vegetable. What you can do, you can pressurize the water a lot. It's like there is a driving force for them to flow in, right? If you just let it go, if they are the same pressure, they have a driving force to lose the water to the higher concentration side, because the water has a lower chemical potential. But now what you do is you pressurize the water, to reverse the flow. Does it make sense? And this is a very qualitative one, but qualitative understanding is also very important. So this is by pressurizing them, the backflow can happen, and so there's no net flow, means they are in the same equilibrium. So that's another way to look at it. But in a way, what I'm saying is, solution is at this pressure. Solvent, they are. So this now. This is I gotta look at this now. Pure at pressure P. pressure P. Yeah. And I just want to make sure that this one is entirely correct, means I want to put that in. I want to define XA. Okay. Well, let me rewrite it this. Okay. So this is not only that. Is a pressure plus extra pressure, osmotic pressure, but that extra osmotic pressure depends on the concentration of XA. So those are the things that is going to compensate in each other. So what needs to happen? This is a solution with an extra pressure head. Right? So this solution, which is represented by concentration, is mole fraction of the solvent. And then this is an extra pressure head, and this composition of solvent, they are related term, and they are in equilibrium with pure water. Because this is a pure water side, only water can go in and out. There's no salt, right? So I should not write it here. I should write it here. There's nothing ions on this side. It's just a simple water. Is allowed to have this,